Okay, welcome back. This is lecture 7, video 2, and we just established a relationship between the growth function and the VC dimension that we define as the largest n that can be shattered because it's actually the tightest bound with the smallest breakpoint. Okay, so having done that, let's look at a few examples of VC dimension with certain hypothesis sets to better understand how the positioning of the VC dimension is, and is it in any way related to something else in the model. So let's look at some of the examples that we've looked at before, of course. So the examples I'm looking at are the 2D perceptron, and then I think the second one was the 1D positive ray, and the rectangle, right? So two-dimensional positive rectangle. Let's look at these hypothesis sets because we are quite familiar with them by now and what happens to each one of them. So here is my n. So n could be 1, 2, 3, 4, 5, 6. And then the VC dimension for each of these. What is the VC dimension going to be? Okay, so if you remember, and then if we would like, we can just like write the 2 to the n here. So that's going to be 2, 4, 8, 16, 32, and so on, 64. Fine. So in case of the 2D perceptron, we saw we could implement 2, 4, 8, and then this was 14. So that was my breakpoint, right? In a one-dimensional positive ray, I saw it was 2 and then 3. So 2 was the breakpoint, right? And in the two-dimensional, we could implement 2, 4, 8, even 16. But although we didn't show how many we can implement, we definitely knew it's going to be less than 2 to the 5, which is 32. So here was the breakpoint. Okay, so in terms of our definition of the VC dimension, if, for example, in this case, 2D perceptron, the breakpoint is 4. So the VC dimension is going to be k minus 1. K here is 4. So this is going to be 3, right? Here, in case of a one-dimensional positive ray, it is going to be, again, the breakpoint is 2. So this is going to be 1, right? And in two-dimensional positive ray, this is 5. The breakpoint is at 5. So this is going to be 5 minus 1. That's going to be 4. Okay. So these are the VC dimensions for these hypothesis sets that we've looked at earlier. Now, if you think about each of these hypothesis sets, for example, the 2D perceptron, the one-dimensional positive ray, and the 2D positive rectangle, what are the number of parameters that we need for the model? For example, the two-dimensional perceptron. So the 2D perceptron, the number of parameters for the model itself, right? So if you remember, there was this W0, right? And then W1, the weights that were there for the two-dimensional would be 3, right? And the number of parameters for the one-dimensional positive ray, if you remember, there was just one-dimensional positive ray. There was just this threshold, right? Which we were, I think, denoted by W0. Don't remember exactly, but I do remember there was this threshold. To the right of that, we consider it's positive. To the left of that, we consider it as negative. So there was just like one parameter that was defining that hypothesis set. And then in case of a rectangle looks something like this. So you can have like x1, y1, and then x2, y2. So basically, this is how you define a rectangle, right? And so for a two-dimensional positive rectangle, the number of parameters that we had were like around, so x1, y1, x2, y2. Now, if you look at the number of these parameters that are required for each hypothesis set, you can say that this is 3, this is 1, this is 4, and this is exactly what my VC dimension is telling me, right? So we can tell just by looking at these 3 simple hypothesis sets that there is some correlation between the number of parameters and VC dimension. So can we kind of create some kind of relationship here, or is it just for this scenario? Well, generally speaking, there could be models that have like very few parameters and the VC dimension could be infinite. And there could be models that have many parameters and VC dimension is 1. So although there is a relationship here, right? So there exists a relationship, but we cannot guarantee that, right? So we cannot always guarantee. And this is evident in these simpler sort of hypothesis sets, but we cannot guarantee that exists. However, like the theory holds for all cases. So you cannot put directly the number of parameters in the error bar, but you can put the VC dimension. And that's why the VC dimension holds more relevance as compared to the number of parameters for that model, right? So we saw that here, that because VC dimension is directly related to, in fact, it is defined based on your breakpoint, you can actually go and replace the VC dimension here within the error bar. And you cannot do the same for the number of parameters of a model, right? So that's why sometimes that relationship is useful, sometimes it exists, but not always. And that's why we are focusing more on the the VC dimension, because in the error bar, that's what we get. So why is that important? Is because if you're looking at this, the order of my error bar, it's the square root of the VC dimension log n over n, right? So if we double the VC dimension, right, we need to, like, if this grows, basically the numerator grows, right, we'll have to do something about the denominator as well, right? So let's say almost double it to get a smaller error bar. Right, so that's how the impact of the VC dimension is on this error bar. Okay, let's look at one more example, which is the convex sets. Now, if you don't remember from one of your optimization classes what a convex set is, it's essentially a set of points such that if you just pick up any 2 points within the set and you join them, then the line stays within the set of points within that set. So basically what I'm trying to say is that this is not a convex set, because the line doesn't, like, I just picked randomly any 2 points, and if I join them, the line goes outside the set of points. So this is my convex set, right? And what I'm looking at as an example is convex sets as my hypothesis set, or maybe to be more precise, positive convex sets. Well, what are those? Basically, whatever points lie inside my convex set is going to be positive. Anything outside is going to be negative, right? And we are trying to figure out the VC dimension of that. So basically, I'm going to check how many points on some dichotomy can be shattered and how, right? So that's what we are looking at here. And so let us assume we have like this, like these points. So this is positive, and maybe this is also positive. These are positive points, and then there is a negative point here, and then again there is a positive here. Okay, I'm drawing really like weird points, and then there is a negative here. Now, if you think about this like convex set as my hypothesis set, what I can do is I can have a circle, right, an imaginary circle, and think of these points as like lying on that, maybe, right? So basically what I can do is maybe have like a point in here and have like these positive points included, right, such that like slightly above that and this positive point is included, and like create some sort of a polygon that would include only the positive points, and the negative one is not. Another way of like looking at this, and a better way rather of looking at it, would be, let me just like erase it. This wasn't the best, I would say, representation. Let me redo that again. Is, let's say this is negative, this is positive. Let me draw it better this time. This is positive and this is negative, and another one more point positive, right? So how are we going to utilize a convex set essentially to include all of this? Basically what you can do is you can imagine that on the negative points you're picking up something slightly inside this, right? And for the positive points you can say that you're picking a point slightly outside this. Yes, this is a better way of thinking about it, right? So when we start like putting these points together, right, so I would definitely come here, but the negative point would go outside, right? So the negative point would not be included essentially, because I've picked a point like a slightly below this, right? So this is a convex. This is a better way of kind of putting it, right? So I've created a convex set in which I've included the positive points because they're just like right inside this. And then I picked points at the negative point They were just like slightly below the actual point. Okay, so no matter what the distribution of the point is going to be, what the alignment or sort of the way the points are given to me, no matter what the data we have, we can arrange them on a circle and shatter them. This is what's happening here, right? So using a convex set, I can shatter almost everything that's given to me. So what does that tell me about my VC dimension? Well, that tells me about the VC dimension that it is infinite, right? So what does this tell us about like this convex sets as a hypothesis set? Well, if you think about the learning process, this is not at all useful, right? So not useful as much as we would like it to be, not useful for learning, right? Doesn't um, really leaves us with a lot of choice because we have to think of everything in terms of the error bar and the relationship between E in and E out. So obviously this is not as useful as we would have liked it to be, right? Okay, so what have we done? Let's summarize it here, right? So we looked at the 2D perceptron, the 1D positive ray, 2D positive rectangles, and positive convex sets, right? And we also figured that there are models with few parameters but infinite VC dimension, and models with less number of um, more number of parameters, so that means like redundant parameters but smaller DVC. So this was like established earlier that there isn't necessarily a relationship as such, but we found out that relationship in some simpler hypothesis sets like the 2D perceptron, the 1D positive ray, the 2D positive rectangles, right? So basically we also found out like in the positive convex sets that the VC dimension and the number of parameters could go to an infinite number because we could just like arrange all the values on a circle and then just like go and shatter them. So what we've done is we have looked at two extremes. One very simple ones which are not as useful in practice. So not useful in practice. And one which is extremely complex. Again, not very useful for learning. So what we are stuck at this point is that are there any useful hypothesis sets that we can really utilize in practice? So that's exactly the question that we're going to answer in the next video, starting in the next video. And I think the first one that we're going to look at is our very favorite model, the perceptron.